Okay. So let me just bring up the exam really quickly. Oh no, this is 370. Okay. So we're going to be going over this exam here. This was the exam that was given, I think it was last semester, yeah, spring 2024. She said that she's fine with people using past exams. She just doesn't give them out, but if you're able to get them, she's fine with that, with you using them. So this is what we're going to use. All right, so we're going to quickly go over question 1. And again, it's the same general format as the practice exam she gave us. First question is the LP problem. Second question is a proof. And the third question is like one of these word problems, which they're generally easy. I think the only tricky thing on this exam was the proof, which this proof is pretty weird, but we'll go over it. I don't really know how to do it either, but I'll try to, we'll see. We'll see how it goes. Okay. So, 1A says to sketch the feasible region and carefully label all extreme points. Solve the problem graphically, being sure to show the objective function in your sketch. Okay, so let me see if this would actually work. How can I turn this? Does it not let me turn it? Wow, then I don't even know what the point of it is if I can't. Oh, there we go. Okay. So we're going to quickly go ahead and make a graph, which I do recommend bringing a ruler to the exam. Okay. And so, can I stretch this out a bit? No. Okay. So I'm going to go ahead and put some points here. So this could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Obviously, this is very rough. You could probably do better if it's like on paper with the ruler. All right, I'll just stick with that for now. And so this is sketch fields reason, okay, and we're going to be using this LP problem here. So we see that we're going to be sketching 3 lines. x1 plus 2x2 is equal to 6, x1 is equal to 4, and negative x1 plus x2 is equal to 0. Obviously, the easiest one would be x1 is less than or equal to 4, right? So, we're going to go to x1, and we're going to set the value equal to 4. So 1, 2, 3, 4. So right here. And we're going to draw that line. Ooh. Okay. So there's that. And then we have x1 plus 2x2 is equal to 6. Well, if x2 was equal to 0, then x1 would be the value 6. So we're going to go in here. I'm going to, first of all, I have to do this. So we're saying, again, if x2 in this value, in this equation here, if that was 0, then x1 would be the value 6. So 1, 2, 3, 4, 5, 6, right there. Hold on. 1, 2, 3, 4, 5, 6. So boom, right there. And then if x1 was 0, then x2 would be the value 3. So 1, 2, 3. So we go here. We're going to connect the two lines. Just like that. Okay. We're going to draw a connecting line. Okay. All right. And so here you can see that it says it's less than or equal to 6. So it's going to be going in this direction. Right? You can identify that because let's say this is a line. Less than is this way. Greater than is this way. So if you were to rotate it some amount of degrees, this will be less than, this will be greater than. That's the case here. And if you were to rotate it this way, like that, this will be greater than, this will be less than. So that'll help you in identifying the region that you have to shade in, the feasible region, sorry. Okay. All right. And then we have the last line, negative x1 plus x2 is equal to 0. Well, if x1 is 0, then x2 is 0. And if x2 is 0, then x1 is 0. Right? So that's just the point 0, 0. So we go here. And there we go. Which that would have been included anyway, so that's fine. All right. All right, so this looks good. And we see that we have an intersection here, so we're going to have another edge right here. And then also, if we check for the 4, we see that it's less than or equal to. So we're going to be going in this direction. Okay. That means that our feasible region is going to be something like this. Okay. All right. Sorry, why am I getting called? Give me 1 second. Okay, I don't know what this is about. Okay, sorry about that. So we graphed all our lines, but now the last line that we have to graph is the objective function. So let's look at our objective function. We have 3x1 plus x2. We need to set this equal to something that both the coefficient of x1 and the coefficient x2 can go into. Or it can be evenly divisible by those coefficients. What we see in this case is going to be equal to 3, because 3 divided by 3 is 1, and 3 divided by 1 is 3, right? So we don't get a decimal. So we're going to be graphing the line. If I go here, 3x1, I'll put it in blue. Three x1 plus plus x2 is equal to 3. Right? That's the exact thing we had here. And so we see that if x2 is equal to 0, then x1 is going to be equal to 1. And if x1 was equal to 0, then x2 would be equal to 3. Okay.
Just a question. How did you get equal to 3?
Yeah, because if you check here, we need to set it equal to something that it can go evenly divisible. It can go evenly divisible into. Obviously, if you wanted to, you can put any value, but putting it something that works for both variables, it's just easier to graph, right? So we see that 3 and the coefficient here is 3 and the coefficient here is 1, right? So we want to find something that can be divided by both of those values and not get a decimal. And that value be 3, because 3 divided by 3 is 1, and 3 divided by 1 is 3. So that's not a decimal. We could do that. That's like the smallest value. If you wanted to, you could do 6, you could do 9, you could do 12. Like, you just
Okay,
need,
that
like, yeah. All right. Okay. So we see that x1 is equal to 1. So we're going to go to 1 over here. There we go. Put 1. And we see that x2 is equal to 3. So we're going to go over here. 1, 2, 3. Right, that's right there. And we're going to graph that line. So go right here. So it's going to be kind of hard to line up. Okay. There we go. And so this is the objective function in the event that k is equal to 3. But now we also need to do in the event that k is equal to 0, right? So essentially what we can do is just copy this line. It might not let me. Oh, okay, there we go. We can just copy this line. It needs to be a line going through 0, 0 that's parallel to this line. So we can paste it. Just like that. And then this would be in the event that k is equal to 0. And this would be our objective function. All right. Obviously, it would span more than this. I just don't want to have to put it through each portion. But this is basically our objective function. And we can use this to see, okay, which extreme point is it going to hit first? Well, first, let's label our extreme points. This is A, this is B, this is C, and this is D. This is not included in this because it's not within the feasible region, right? So this one is not an extreme point, okay? And then we can label the points. Oh, sorry, the values of these points. So we have A. We already know that A is 0, 0. We have B. We already know that B is 1, 2, 3, 4, 0. C. We don't entirely know the value of C, so I'm going to keep that blank for now. And D, we know the value of D. It's 1, 2, 3. It's 0, 3. Okay? And so to get C, we have to treat these two lines again as equations, where we could think of this is our first line and this is our second line. And we have to add them in some way so we can get that value. So what we can do is, remember this one was x1 is equal to 4, and this one was x1 plus 2x2 is equal to 6. So x1 plus 2x2 is equal to 6, and x1 is equal to 4. So what we can do is we can subtract the x1s, or subtract the whole thing. We get 2x2 is equal to 2. Divide by 2 on both sides. We get x2 is equal to 1. Okay? And then we can find the value of x1. Well, we can use this function up here, where we see that we have x1 plus 2x2 is equal to 6. Well, we know x2 is 1, so here we're essentially saying x1 plus 2 is equal to 6, or x1 is equal to 4. Right, because we took that 2, subtracted it on both sides, and we got x1 is equal to 4. So now we have our point 4, 1. So we go here, 4, 1. And we can verify that by looking at the chart. We see 1, 2, 3, 4, and then 1, and that is our C value. Okay. So these are our, what's it called? These are our extreme points, right? A, B, C, and D. And we can see which one's the last one to get hit by, again, just popping out the ruler. It's the exact way it should go, like that. And we see that A is the first one to get hit, then B, then D, then B, then C. So we know that C is going to be the maximum, but we can verify that by using the objective function with these values. So remember, our objective function was 3x1. Let me just go back to it. I think it was 3x1 plus x2. Yeah, 3x1 plus x2. Okay. And so what we're going to do is we're going to plug these x1 and x2 values into this objective function and see what we get. So here we're going to get 0 plus 0. That's 0. Here we're going to get 4. Here we're going to get 3, 4 plus 0. That's 12. Here we're going to get 3, 4 plus 1. That's 13. And here we're going to get 3, 0 plus 3. That is 3. And so we see that 13 is the max. And obviously, remember, we said that C is the last one to get hit. So C is the winner. And we were able to verify that here. So at this point, we solved it graphically. We found the maximum value. And obviously, again, they were looking for the maximum as stated here. So that answers part A, right? Where we wanted to label all the extreme points and solve the problem graphically. And obviously we needed to also be sure to show the objective function in your sketch. So that's what we did here as well. Okay. So any questions about that so far? Does that make sense?
Yes.
Good. Okay. So now we can move on to B. Actually, I'll put a, this was part A. Hold on. This was part A. And now B says to express the feasible solution 2, 1 as a convex combination of the extreme points. Well, let's see. Where's 2, 1? 1, 2, 1. So 2, 1 is right here. Put it in a rainbow. 1, 2, 1. Oh, never mind. I'll put it in yellow. 1, 2, 1. So this is 2, 1. So we see it's obviously in the feasible region. And you can use that as a way to kind of confirm what your feasible region is. Because let's say you accidentally did it like up here, right? For some reason. I don't know why, but let's say you were to do that. You can confirm if that is correct by looking at part B of the question to see, okay, is this point within that region? There is a possibility that, you know, that point can still be the region, but you can just use that as kind of like, you know, some reassurance that you're correct. It's not 100%, but some level of reassurance. Because it even says express the feasible solution 2, 1. So it's saying it is a feasible solution. Okay. So that's 1, 2, 1, 2, 1. And now to express the feasible solution as a convex combination of extreme points, we need to take some of the extreme points, right? And then add them together by some scalar multiples. Actually, what do you even say scalar multiples? By some multiple values, right? And so the easiest way to do this is to use the x-axis and y-axis values, because this will allow for like more zero values within your multiplication, and that will cause for easier math. You just have to make sure that it would be in the same region. So let's say we wanted to do ABD. we need to make sure, okay, if we do ABD, in that triangle, is 2, 1 still there? It is, right? Let's say we wanted to do ADC. Well, let's see. If we wanted to do ADC, let's do A and C, and we see that this also works, right? But if we wanted to do ABC, this wouldn't work, right? Because AB, they do connect, BC, they do connect, and AC, they do connect, but 2, 1 is not within that triangle. It's on the outer part. So you need to make sure that it actually lies within the points that you're using. So for this example, we're going to use A, B, and D because they work, and also they're X and Y axis points, so they cause for easier math. Okay, so I'm going to go over here, and this is going to be part B. Remember, we're doing 2, 1. So we're going to have A, which is the point 0, 0. We're going to have B, which is the point 4, 0, I believe. And I think it was C 0, 3. And let me just double check. Sorry, not C, D. D 0, 3, B 4, 0. Okay, yeah, so let me just put D instead by mistake. Okay. All right. So we basically want to distribute these variables. So we're going to get that 2, 1 is equal to 0A, 0. Actually, yeah, okay, that's fine. Plus 4B, 0B, plus 0D, 3D. Okay. And so what this is saying, we're saying, okay, 0A, this portion here, plus 4B plus 0D is equal to 2. And 0A plus 0B plus 3D is equal to 1. So we can map that out by saying again, I'll do it this way. We are saying that 0A, which 0 times A, 0 times anything is just 0, so we don't even have to write it. We can just put nothing there. Plus 4B plus 0D, again, that's just 0, so we don't have to write it, is equal to 2. Okay. And then, wait, hold on. Oh, no, okay, this is correct. Okay, sorry, my fault. And then from here, we also have that 0A plus 0B plus 3D is equal to 1. So that's just 3D is equal to 1, which you can kind of see why it's better to use the X and Y axes, because you see how many zeros or values are getting just kind of canceled out because we had a 0. If there wasn't a 0 there, then we would have to do a whole system equations solution, and that would have just been a whole mess. Okay. And then also, whenever you are finding the convex combination of extreme points, you also have to note that the summation of these variables A, B, and D must be equal to 1. Okay, so we're also going to write A plus B plus D is equal to 1. And then finally, all these values must be non-negative. So A, B, D is greater than or equal to 0. If you do not put those things, you more than likely will not get credit. Okay. Just give me 1 second. Okay. Yeah, you will more than likely not get credit. So please make sure to do that. All right. So with this, we can see that b is equal to 1 over 2. We see that d is equal to 1 over 3. Okay. But now we say, okay, what is a equal to? Well, we're going to use this equation to find out. That's the reason why we had this. We have that a is equal to, we have that a is equal to 1 minus 1 over 2 minus 1 over 3. Okay. And with this, we can use 6 as a common. So we're going to get 6 over 6 minus, that would have to be, I think, just 3 over 6 minus 2 over 6. Yeah, I think that's correct. So 6 minus 3, that's 3, minus 2, that's 1. So we're going to get 1 over 6. So a is equal to 1 over 6. And then we can rewrite it over here. A is equal to 1 over 6. B is equal to 1 over 2. And D is equal to 1 over 3. Okay. And of course, you can double check your work, because we could say, okay, 2 must be equal to, let me put this back. Okay. We know that 2, again, must be equal to 0a plus 4b plus 0d. We plug in the b value, we plug in the b and a value, we get 0 plus 2 plus 0, we get 2. And 1 must be equal to 0a plus 0b plus 3d. Plug in the values, we get 0 plus 0 plus 1. So 1 is equal to 1. And this is correct. Okay. All right. And so that's the answer to part B. Now, part C, it says put the LP problem into standard form. This is pretty simple to do. Let me go like this, C. And what I'm going to do is I'm first going to rewrite the original problem. So we have max K is equal to, and I'll zoom back in after I finish writing it just so I can see it. K is equal to 3x1 plus x2, such that x1 plus 2 plus 2x2 is less than or equal to 6. X1 is less than or equal to 4. Go down a bit. Negative x1 plus x2 is less than or equal to 0. And x1, x2 is greater than or equal to 0. Okay. So let me zoom back in now. Probably have some better handwriting now that I'm zoomed in. There we go. All right. So when we are, hold on, let me make sure I open the chat. So the denominators must be the same. Are you saying with when we were doing the over here, this stuff over here? Yeah. So when you're doing fraction like arithmetic, the denominators must be the same in order to work with the values at the top. So the numerators. So basically we made them the same, and at that point we were able to just keep the denominator the same, and at the top just say 6 minus 3 minus 2, that was 1, and we just got 1 over 6. Yeah. But if you don't know how to do that, you'll have your calculator on you, so you'll be fine. All right. So with standard form, we know that 1, all values must be greater than or equal to 0. 2, we must be in minimum, not maximum. And in the event that we are in maximum, we turn it into minimum by negating the objective function. And thirdly, we can't have any inequalities like this. So less than or equal to, greater than or equal to, we have to instead only have equal signs. Okay. So we're going to say, since this is max, we're going to turn it into min. So min. And then whenever we're doing min, we usually do z. So min z, but it's fine if you keep k, I believe. And again, we want to negate that value. So we're going to say negative 3x1 minus x2. Such that x1 plus 2x2, and now we see we have a less than or equal to sign. If we have a less than or equal to sign, that means that obviously this current value is potentially less than what's on the right. So it's potentially less than 6, right? And so to get it to be equal to it, we need to add some value. We don't know what that value is, but we must add some value to x1 plus 2x2 to make it equal to 6, for sure, right? And so we can just, for now, say plus x3, right? And that plus 3 will handle that for us. So now we'll have equal to 6. We don't know the value of x3. We just know that it's some positive value that'll ensure that we will be equal to 6. So like, let's say the value of x1 plus 2x2, let's say from that we get the value 3. That means that x3 will have the value 3 because we want it to be equal to 6. Another example, let's say x1 plus 2x2 is equal to 5, and x3 is going to be equal to 1. Okay? So, next one, we have x1. Again, we have another less than or equal to here. So we're going to add another one of these variables plus x4. You cannot reuse the same variables. Let's say if you already use x3, you can't use it. You can't use it again in another equation. You have to use another variable. So here we're using x4, and that we want equal to 4, right? For the 4 right here, and then finally negative x1 plus x2. We have a less than or equal to, so we're going to put plus x5 is equal to 0. Okay. And now, again, remember we needed for all of the variables to be greater than or equal to 0. We know that x1 and x2 are already greater than or equal to 0, but we also just added x3, x4, and x5. So we must also say that those are greater than or equal to 0. So x1, x2, x3, x4, x5 are all greater than or equal to 0. And this is now in standard form. And this answers part C. Okay. And we're going to continue working with this. All right. So now part D says, okay, find the basic solution involving x2, x4, and x5, where x4 and x5 is the slack variable for the second inequality, and x5 is the slack variable for the third inequality. This will be given in a question. You can kind of use that as a way to confirm your answers, where here it says, okay, x4 is the slack variable for the second inequality. Well, let's check. Is it? This is the first, this is the second, so x4 is the slack variable for the second inequality. Okay, let's check what it said here. x5 is the slack variable of the third inequality. So we can go to the third inequality, 1, 2, 3. x5 is the slack variable for the third inequality, which I forgot to mention. These extra variables that we created, they're called slack variables. Okay. And so again, we want to find a basic solution involving the two slack variables x4 and x5 and the variable x2. And we want to say, okay, is it a feasible solution? What this is basically saying is take the variables that are not in the base or not involved in the basic solution. So in this case, x1 and x3, set them equal to 0, and then find the values of x2, x4, x5. So I'm going to do that over here. I'm going to put, this is part D. And again, x1, x2, x3, x4, x5. And remember, we're going to set x1 and x3 equal to 0. So now we need to find the values of x2, x4, and x5 using the standard form that we just created. Well, if we plug in x1 and x3 into the first inequality, right, or sorry, the first equation, sorry, we get 0 plus 2x2 plus 0 is equal to 6, meaning that x2 is equal to 3. Similarly with x4, if we plug in x1, we get 0 plus x4 is equal to 4. So x4 is equal to 4. Okay. And then with x5, if we plug in x1, we get 0 plus 3 plus 5, plus x5 is equal to 0. So again, that's just 3 plus x5 is equal to 0, meaning that x5 is equal to negative 3. Okay. So we have just found the values of x1, x2, x3, x4, x5. Right? That was the basic solution we needed to find. And we need to say, okay, is it a feasible solution? Well, if you remember with a feasible solution, all of the variables need to be non-negative. Are all these values non-negative? No. x5 is less than 0. So this is not a feasible solution, as all variables are not greater than or equal to 0. Let's say if x5 was the value 0, then this would be a feasible solution. But since it's not, or sorry, if x5 was just anything greater than or equal to 0, then this will be a feasible solution. But since it's not, then this is not a feasible solution. So that is the answer to D. Okay. All right. So now we can move on to E. Solve the linear programming problem by the simplex method. So to do that, we need to take this standard form we just made and turn it into a tableau. So I'm going to put part E here. Usually these are pretty long. Let me go down like that. Okay. So remember, we're working with x1, x2, x3, x4, and x5. And then along the bottom we have, or sorry, along the side we have 6, 4, 0. And then we're going to put the values of the coefficients for each of these values in each equation. So x1 here we have 1, then we have 2, then we have 1, 0, 0, 1, 0, 0, 1, 0, -1, 1, 0, 0, 1. Okay, so this finished the top portion of the matrix we need to make. And the bottom, we need to put the objective function. So that's -3, -1, 0, 0, 0, z. And that is our tableau that we're going to be working with. Okay. And so for this tableau to be in a feasible canonical form, for us to get a solution, we need to have a 3x3 identity matrix somewhere within this tableau. Zeros below each column of that identity matrix, so 0, 0, 0, and non-negativity on the right side. Right, so we can't have any of these values be less than or equal to 0. Sorry, we can't have any of these values be less than 0. Right, so if that 6 was the value -1, then this would not be in feasible canonical form. Okay. Alright. And so, since this already is in feasible canonical form, we can find a basic feasible solution by identifying the basic and non-basic variables. Well, the basic variables are the ones involving the 3x3 identity matrix. So B, 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 that identifies basic. And non-basic are the ones that are not involved in that. So we can put an N. And so to find a solution, we identify the variables. So x2, x3, x4, x5. And we're going to set the non-basic variables equal to 0. So x1 is 0, x2 is 0. Right? So we're kind of cutting this portion out. Okay? And then from there, we use that to identify the values of x3, x4, and x5. If we go along, we see that x3 is equal to 6, because you can think of this as x3 plus 0 is equal to 6. x4 is 4, because you can think of it as 0 plus x4 plus 0 is 4. x5 is equal to 0, because you can think of this as 0 plus x5 is equal to 0. So, we have 6, 4, 0. And this is our first solution. But we can see, okay, is this solution one of the extreme points? Well, we have x1 is equal to 0 and x2 is equal to 0. So let's check. We see A is 0, 0. So this is the solution for point A. Oh, where am I? This is the solution for point A. So let's identify that. This is point A. And we can find the value of this by, again, remember this portion down here. This is saying that z is equal to -3x1 minus x2. Remember that x1 and x2 are equal to 0, so that means z is equal to 0. So, from this, we know that the point A equates to the value 0. Okay? Oh, I'm going to do that. Alright. So that's how we found the first solution. But this is not the optimal solution. We know we're at the optimal solution when we have non-negativity in our objective function. Here we have a -3 and a -1, so we are not optimal. So to find or to get closer to the most optimal solution, we're going to swap the column containing the lowest coefficient here, in this case -3. We're going to swap this with one of the basic columns. So again, we're going to swap this, right, with either x3, x4, and x5. So how do we identify which one to swap? Well, scissor gives a shortcut to do it. I personally don't like doing the shortcut because it can mess you up. So to do it, you can just match up each value for x1 with each basic variable. So we have 1x1, so x1, go across, we hit x3, plus x3 is equal to 6. Then we have x1 plus x4 is equal to 4. Then we have negative x1 plus x5 is equal to 0. Okay. And we're going to see, okay, what is x3 equal to? x3 is equal to 6 minus x1. x4 is equal to 4 minus x1. And x5 is equal to 0 plus x1, so that is just x1. Okay. And for each of these variables, we want to see, okay, how high can x3, x4, and x5 go if x1 increases? Well, remember that x3, x4, and x5 must be non-negative, right? So we want to see, okay, how high can x1 go without turning x3 negative? Well, for this first one, x3, we know that the most, I guess the closest we can get to becoming negative without becoming negative would be to 0, obviously, right? Because right after 0 we have negative 0.1, right? Or whatever you want to say, negative 0.000, like all the way infinite, right? So the closest we can get to it is 0. So what we can get for x1 here is 6, because 6 minus 6 is 0. Similarly for x4, the closest we can get to is when x1 is equal to 4. And with x1, the highest we can go without turning x5 negative is infinity. That's because x5 is equal to x1. And if we're infinitely increasing x1, x5 will never become negative. So that's why x1 can increase forever. Okay, but we want to find which one can increase the smallest. In this case, it is x4, right? Because the value for x1 and x4 is 4, and the value for x1 and x3 is 6. 6 is greater than 4, so x4 is our candidate. So we want to use x4 to swap. Okay. So we're going to be swapping these two columns. Now, when I mean swap, I don't mean like physically swap them. What I mean, actually, let me go like that. What I mean is we want x1 to now go into the identity matrix as if it was x4. So we want x1's column to become 0, 1, 0, 0, because that's the values that are in x4's column. And we can do that with some simple identity, some simple arithmetic or matrix manipulation. Sorry. So I'm going to bring this down here. Ooh. And obviously, since x4 is 0, 1, 0, 0, the obvious candidate for x1 would be the 1 right here. This is going to be our pivot, this 1 over here. And so I'm going to redraw this matrix, x1, x2, x3, x4, x5. We know that this row here is going to be unedited because we already have the 1 where we want it. So we're going to draw 1, 0, 0, 1, 0, 4. Okay. And we want, let me identify that this is the pivot. We want to turn the 1 above this 1, so the 1 up here, we want to turn that into a 0. We can do that by doing R1 minus R2. Okay. That's going to give us, well, 1 minus 1, that's 0. 2 minus 0, that's 2. 1 minus 0, that is 1. 0 minus 1, that is negative 1. 0 minus 0, that's 0. And 6 minus 4, that is 2. And you can already see that x4 is no longer a basic variable because not every value in its column is 0, 1, 0, 0, or not every value is one that can be found in an identity matrix column. Okay. Additionally, we want to turn this negative 1 into a 0, so we're going to do R3, which R3 indicates row 3, R3 plus R2. So we're going to have negative 1 plus 1, that's 0. 1 plus 0, that's 1. 0 plus 0, that's 0. 0 plus 1, that's 1. 1 plus 0, that's 1. And 0 plus 4, that's 4. Okay? And then finally, we want to turn this negative 3 into a 0. So we can do R4 plus 3 R2. Okay? So that's going to be negative 3 plus 3, that's 0. Negative 1 plus 0, that's negative 1. 0 plus 0, that's 0. 0 plus 3, that's 3. 0 plus 0, that's 0. And then z plus 3 times 4, that is z plus 12. Okay. So I'm going to redraw our matrix correctly here. Oh, fuck. Hold on. Okay. And so you'll realize that now x1's column is now 0, 1, 0, 0. And the other basic variable columns, 1, 0, 0, 0, and 0, 0, 1, 0, are not touched at all, right? They're still basic variables, or they're still candidates for an identity matrix, or 3x3 identity matrix, right? And so let's identify our new basic variables. We have b, b, b on x1, x3, and x5. And then non-basic, non-basic. All right, so we can see that x1 has become basic and x4 is no longer basic. And now we have to say, okay, well, is this, let me move this over. Well, you want to be annoying, don't you? Okay. I'm just gonna, there we go. Okay. So now that we're in this form, we have to say, okay, is this in feasible canonical form? Well, everything on the right side is greater than 0, or greater than or equal to 0. We do have a 3 by 3 identity matrix, right? 0, 1, 0, 1, 0, 0, 0, 0, 1. And we have zeros under each of the columns of that identity matrix. So we are in feasible canonical form. Since we are in feasible canonical form, we can come up with a solution. So we're going to say x1, x2, x3, x4, x5. We're going to set the non-basic variables to 0, so x2 and x4. And we're going to get the values for x1, x2, and x5. Well, x1, we see that that is 4. X3, we see that that is 2. And then x5, we see that that is 4. And we see that none of these values here are non-negative. So this is a feasible solution. Okay. And now we have to identify, okay, is this one of the extreme points, 4, 0? Well, let's check. 4, 0 equates to point B. Okay. Let's go down. Point B. Okay. Okay, and then we can see, okay, what does B equate to? Well, we know that Z plus 12 is equal to negative x2 plus 3x3, right? But we again know, oh sorry, not x3, x4. We again know that x2 and x4 are already equal to 0. So we're getting Z plus 12 is equal to 0. So Z is equal to negative 12. So this B value here is equal to negative 12. You might notice if we go back to B, we see, okay, well, B here was supposed to be 12, not negative 12. Well, remember, the minimum is the negation of the maximum's values, right? And so, oh wait, I just realized my, oh, there we go. I just realized my headset was dead the whole time. Sorry, what happened? Did someone say something? Oh, no, okay. So yeah, remember, the minimum is the negation of the maximum's values. So if I go here, right, min, this would be 0, negative 12, negative 13, negative 3. So negative 12 is correct. Okay. But we say, okay, well, is this the optimal solution? Have we finished? Well, remember, if we want it to be optimal, all of the values in the objective function must be positive, right? Obviously, that's not the case here, because we have a negative 1 right here. So we have to swap with the column that contains the lowest value within the objective function. In this case here, it's negative 1, so we're going to swap with x2. Okay. Let's go like this. All right, and then we have to identify, okay, what basic variable is x2 going to swap with? Well, we have 2x2, 0x2, x2. This 2x2 is associated with this x3, so plus x3 is equal to 2. This 0x2 is associated with this x1, so plus x1 is equal to 4. And then this x2 here, this 1x2, is associated with this x5 over here. So plus x5 is equal to 4. Okay. And obviously this question can be done way faster. We're taking a lot longer so I can kind of explain it each step. But from here, we're going to have x3 is equal to 2 minus 2x2. X1 is equal to 4, right, because that's just 0. And x5 is equal to 4. Actually, I'll put minus 0x2 just to show it. 4 minus x2. Okay. Well, the highest value that x2 can go here is 0, right? Because if you go any higher than 0, then x2 will become negative. The highest value that x2 can go here is infinity, right? Because you're multiplying infinity by 0, that's just 0, and x1 is still just 4. Right? So x1 will never go negative. And then x5, the highest value that x2 can go is 4. So x3 is the min. Or the one containing the min, I guess you want to say. So we're going to be swapping x2 with x3. Okay. And let's check here. x3 contains the 1 in the first column. All right, so we want 2, 0, 1, negative 1 to become 1, 0, 0, 0. Obviously, the first thing you identify from that is that we could say, okay, that's a 2 that needs to turn into a 1. So we need to take that column and we need to divide it by 2. Okay. So I'm going to draw a line. We're going to get x1, x2, x3, x4, x5. And we're going to do 1/2 R1. It's going to give us 0, 1, 1 over 2, negative 1 over 2, 0, 1. And then we can fill in the rest. 0, 0, 1, 0, 4, 0, 1, 0, 1, 1, 4. Zero, negative 1, 0, 3, 0, z plus 12. Oof, I didn't mean to do that. Okay. So we have the 1 there now, so this is now a valid pivot. Okay. And then we can get rid of the 1 here by doing R3 minus R2. And we can get rid of the negative 1 here by doing R4 plus R1. Oh, wait, no, sorry. We can get rid of the 1 here by doing R3 minus R1, and get rid of the negative 1 here by doing R4 plus R1. Okay. So let me zoom out a bit. Okay, and remember we said R3 minus R1, and R4 plus R1. So x1, x2, x3, x4, x5. We know that nothing's going to change with R1 anymore, so 0, 1, 1 over 2, negative 1 over 2, 0, 1. And remember, we're doing R3 minus R1. So 0 minus 0. Actually, wait, we don't need to do anything with R2 either, so let's just draw that, or write that really quickly. Okay. So R3 minus R1, that's 0 minus 0, that's 0. 1 minus 1, that's 0. 0 minus 1 over 2, that's negative 1 over 2. 1 minus negative 1 over 2, that's 1 plus 1. 1 plus 1 over 2, that's 1.5, which is 3. 3 over 2. Right, because remember, 1 minus negative 1 over 2, that's 1 plus 1 over 2. And then 1 minus 0, that's 1. 4 minus 1, that's 3. Okay. And then R4 plus R1, that's 0. Minus 0 plus 0, that's 0. Negative 1 plus 1, that's 0. 0 plus 1 over 2, that's 1 over 2. 3 minus 1 over 2, that is 2.5. So that is 5 over 2. Right? Yeah, okay. And then 0 plus 0, that's 0. And z plus 12 plus 1, that's z plus 13. Okay. So now let's draw our parentheses. Can I make this smaller? Okay. And now we say, okay, well, is this in feasible canonical form? Well, we do have the 3x3 identity matrix right here, and right here. We have zeros under the identity matrix. We have non-negativity on the right side. So this is in feasible canonical form. So let's identify our basic variables and our non-basic, and let's get our values. So x1, x2, x3, x4, x5. Set our non-basic to 0. And we see that x2 is equal to 1, x1 is equal to 4, and x5 is equal to 3. Okay. And we see, okay, well, is x1 is equal to 4 and x2 is equal to 1? Is that one of the points? Let's see, 4, 1, we see that is the point C. So let's go down. And this is the point C, right? We see, okay, well, what is Z equal to? Oh, sorry, what is C equal to? Well, that's C plus 13 is equal to 1 over 2 x3 plus 5 over 2 x4. We already know that x3 and x4 are equal to 0, so that's z plus 13 is equal to 0, or z is equal to negative 13. So c is equal to negative 13. Okay. Now we say, okay, well, we know that c is equal to negative 13. We proved that with the graph already as well. But is this the most optimal? Well, remember, we said that it's the most optimal when all the values in the objective function are greater than or equal to 0. Here we now have 0, 0, 1 over 2, 5 over 2, 0, which those are greater than or equal to 0. Okay. So this is the optimal solution, which I think that is part F. Let me double check. Yeah, justify the simplex method's stopping rule, test for optimality for this problem. So we already have solved the LP problem by the simplex method, so now we're going to do part F. So, go over here. All right, this is F, and this is the optimal solution. Okay. Why, you may ask? Well, we're going to be using the stopping rule. The stopping rule says if all of the part you will take me forever on the exam. Yeah, it takes really long. It takes me even longer since I'm like verbally explaining each part of it. Hold on, give me 1 second. I'm getting a call. Okay, sorry about that. So yeah, this is the optimal solution. Why? Because all of the coefficients within the objective function are positive. What does this mean? Well, if all of the coefficients in the objective function are positive for each of for each of those variables within the objective function, if they were to increase, sorry, my mic was muted. I was talking. But yeah, this is the optimal solution because in the objective function, if all of the coefficients for each of the variables are positive, then if x1, or sorry, if those variables were to increase, right, then the value of that objective function will also increase. But we're trying to find the minimum value, so we don't want to increase. So if we were to increase, we'd be going in the wrong direction. We don't want to go in the wrong direction. That's a step in the wrong direction. So this is the most optimal solution. So we can write, we already know that z plus 13 is equal to 1 over 2 x3 plus 5 over 2 x4, right? So all coefficients of the objective function are greater than 0. So if either x3 or x4 were to increase, right? Because currently, or sorry, we can say were to go positive, because remember x3 and x4 are both 0 right now. Were to go positive, then z would become greater than negative 13 rather than being equal to negative 13, right? We don't want to increase. So you could put this is a step in the wrong direction. So this is the most optimal solution. Sorry, my handwriting is really bad on this tablet. But yeah, that's pretty much what the stopping rule is. Where if either x3 or x4 were to increase, then z would become greater than its current value, which we don't want that to occur because we're trying to find the minimum. All right. And so that's a step in the wrong direction. So this is the most optimal solution. Okay, because if we were to go in the wrong direction, we're only going to go in the wrong direction after that. So, we don't want that. Okay. Part F is pretty much like a copy paste. You can honestly just memorize like what she's put as an answer in lecture, and then just write that down, and you'll get points for it. Yep, no problem. All right, so this is the answer to number 1. All of that work. This is 60 points on the exam. So if you got this, you get a 60. Just don't spend the entire exam doing this, or else you're only going to get a 60. But yeah. Yeah, this whole question is 60 points on the exam. I think part 2 is like 20, and part 3 is also 20 or something like that, if I remember. 60, 20, 20 makes it 100. But yeah, that's number 1. Now, let's check out the other ones. Oh wait, where is it? Okay. So this is number 2. Now, I did this one before. I don't entirely understand it. I'm gonna have to try to vaguely go off my memory. But we'll see how it goes. Let me just make sure this is all. Yeah, this needs to be smaller. Make it smaller so I could send it to people later. Yeah, way more smaller. What the fuck is happening? All right. All right. So on our exam, remember number 2, we're going to have a proof. For that proof, you have to be able to understand what convexity is. And so that's what we're doing here, where we want to consider the linear programming problem in standard form. So we're given a linear programming problem, and it already is in standard form, i.e., the minimum z is equal to c transpose x, such that ax is equal to b, and x is greater than or equal to 0. Okay? I want to prove that the set of all feasible solutions to this problem is a convex set. Okay? So there's a lot of words here. But yeah, we're just going to have to kind of think this through. So remember, with convexity, what that means is within some set, there are at least 2 points in this set that can be a convex multiplication, convex combination of each other to equal that set, that point. So let's say we have the point, or the feasible solution y, and the feasible solution z are within this set, and then we have some point w that are within this set. You should be able to make a convex combination of y and z and have that equal to w, right? And so to be within that, or to be a feasible solution, let's say that y is a feasible solution, then in this case, ay must be equal to b, and y must be greater than or equal to 0. And let's say for z, az must be equal to b. Actually, I should probably use something other than z because it already says min z. I'll use there's not a lot of variables here. I'm very picky with my variables. We'll do I and j because we're computer science, right? We know what I and j is. So I and j. So let's say I is a feasible solution. So ai must be equal to b, and I must be greater than or equal to 0. And aj must be equal to b, and j must be greater than or equal to 0. Okay? So I'm going to say let I, j, be a feasible solution. Okay. Then, in this case with I must be greater than or equal to 0. I should put a comma instead. And ai must be equal to b. And with j, must have j is greater than or equal to 0. And aj must be equal to b. Okay. All right. So, I'm trying to remember where I go from here. Oh yeah. So now we must say, okay, let's assume we have a point W, which is also a feasible solution. We must show that a W is equal to B. W is greater than or equal to 0. And that W is a convex combination of I and J. Well, to be a convex combination of something, you must have that W is equal to pi, I think it's, sorry, not pi, lambda I plus 1 minus lambda J. I think it's something like that. Again, I'm just going completely off memory. But yeah, it was something like this. Let me just double check really quickly what I had put, because I don't want to say something that's incorrect. And I just got this off of the exam answers. This is not something I would have been able to do on my own either. I know when people took this, most people got this question wrong because people just didn't know how to answer it and people got really mad about it. So I don't know if she'll give this again, but we'll see. So let me just double check what I did. And I apologize for the noise. Okay. Yeah. So again, we have to let yeah, sorry, we don't have to show that W is equal to that. We just have to let W equal that. And then show that AW is equal to B. And there's just so much noise happening downstairs right now. I'm so sorry. Average Dominican household. Okay. I don't know if you guys can hear that, but it'll probably show up in the recording. So let's put this over here. Oh, hold on. Okay. So we're going to let. Ooh, why is that so small? little tiny. We're going to let W equal a convex combination of point I and J. Okay? All right? And so we need to show that AW is equal to B and that W is greater than or equal to 0. Okay? So let's do the first one first. Show that AW is equal to B. So I'm going to show that AW is equal to B. Well, we know the value of W. Let's plug it in. A lambda I plus 1 minus lambda J is equal to B. Okay. Now we can distribute that A. So that's going to look something like lambda AI plus 1 minus lambda AJ is equal to B. Well, what did we say before? We said that AI is equal to B, and we said that AJ is equal to B. Right? If you check up here, AI is equal to B, and AJ is equal to B. So we're going to substitute those values. Where lambda B plus 1 minus lambda B is equal to B. Did that make sense what I just did? Did it make sense how I substituted those B's? All good? You guys have to unmute your mic. You can just type in the chat.
Yeah, that
Makes sense? Yeah. Okay. So from there, we're going to distribute. Where we have lambda B plus B minus lambda B, that's equal to B. Well, from here, that cancels, and so we get B is equal to B. And so we've proven that AW is equal to B. That's the first part of the proof. Now the second part of the proof is that we must prove that W is greater than or equal to 0. Well, remember we know that we'll show that W is greater than or equal to 0. We know that W is lambda I plus 1 minus lambda J. And I will just note that it's 0 less than or equal to lambda less than or equal to 1. Okay. And we must show that that is greater than or equal to 0. Okay. Well, we already know that lambda is some value that is greater than or equal to 0, right? Because it can be between 0 and 1, right? So we already know that this is some value greater than or equal to 0. And then 1 minus lambda, right? We know that the max that lambda can be is 0. And the minimum that lambda can be, the max that lambda can be is 1. And the minimum that lambda can be is 0. Meaning the max that this can be, the minimum that this can be is 0. And the max that this can be is 1. So this is also greater than or equal to 0. Okay. And now from this, if you refer back to the definitions we put up here, we said that I is greater than or equal to 0, and J is greater than or equal to 0. So if we go over here, we would have some value that is greater than or equal to 0 times some value that is greater than, oh wait, I forgot to put the plus sign, times some greater than or equal to 0 plus some value that is greater than or equal to 0 times some value that is greater than or equal to 0 must be greater than or equal to 0. Well, if this is something greater than or equal to 0, plus this is something that's greater than or equal to 0, greater than or equal to 0, then that is something greater than or equal to 0 that must be greater than or equal to 0, which that is the case. Right? And so we've just proved that W is greater than or equal to 0. So that's correct. And so with this, we have proven that since W is able to be a convex combination of two feasible solutions I and J, and that W is greater than or equal to 0, and AW is equal to B, that has proved that the set of all feasible solutions to this LP problem is a convex set. Right? Because all convex combinations of this set is also a feasible solution. Sorry, the set of all feasible solutions, so all feasible solutions within that set, every convex combination of those values is also within that set, so it's a convex set. And so, that's it. that's all you really gotta do. So from there, you could say Q, E, D. Right, so if she were to give this is a pretty easy question to remember. If she were to give this without people seeing this beforehand, this would be a pretty hard question to answer. But you guys have seen it, so you guys have upper hand. So if she gives it, you'll know what to do. Yeah, this is the answer. Any questions about this? Any questions at all?
So basically, we have to memorize the solution.
I
for
mean,
this question, right?
it would help, but it would be more helpful to actually understand why it's correct. Like you should be able to understand, like, to be in a convex set, there must be some point that's a convex combination of two other points within that set. That's how we got lambda y plus 1 minus lambda j. Right? Knowing that will help in answering other questions. You can take the route of memorizing every proof she's given us, including this one, which she hasn't given us. But then let's say you go to the exam and you get a question that we haven't seen yet, then you're going to be screwed because you were just memorizing it. So actually being able to understand why this works, that'll help. I think this one's a great question. I wouldn't be surprised if she gave this. She gave this on last semester's exam. I don't really know what else she can give besides this and the question proofs she's already given. But yeah, if you wanted to, you can like memorize this. That's really up to you. And then if you get something, try to use that combined memory of the stuff that you've memorized to try to answer it. That's also a way you can do it. But yeah, that is that question. Any other questions about this one? No?
No.
Okay. So now let's move on to the last question. And we'll call it a day. It's already almost at 2 hours. All right. Just make sure we're like relatively the same size. We are not. Okay, so let's go like that. All right. So we are given that company X has signed a contract to provide company Y with 300 units of item A, 450 units of item B, and 380 units of item C. Notice how it doesn't say at least 300 units of item A, at least 450 units of item B, and at least 380 units of item C. the company Y wants exactly 300 units of item A, 450 units of item B, and 380 units of item C. Okay? Now, company X can either make these items or purchase them from a distant wholesaler. Okay? If company X makes a unit of item A, so if they make it themselves, it will require 2 hours of labor and 20 Q units. We don't know what Q is, that's just something. Or it can purchase a unit of item A for $200. Similarly, company X can make a unit of item B, right? Make it themselves, and it can make a unit item C. Oh wait, sorry. Make a unit of item B, which requires 6 hours of labor and 15 Q units. Or they can purchase that from a wholesaler for $265. And it can make a unit of item C, which requires 3 hours of labor and 22 Q units, or purchase a unit of item C for $235. Now, on hand, Company X has available 4,000 hours of labor, right? So we must ensure that our production does not exceed 4,000 hours. And each of those hours, they're paying a rate of $20 per hour. And they have available 5,000 units of Q. So obviously we can't go over 5,000 units of Q at $5 per unit. So they're using $5 every time they use 1 unit of Q. Okay. Now the company only pays for the hours of labor and Q units that it uses, right? So let's say they have 2,000 units of Q left over. They're not going to pay for that, right? They're only paying for what they use, similar to the hours. Makes sense. Company X needs to determine how many of each item it should make and how many it should buy in order to minimize its cost while satisfying its contractual obligation. Right off the bat, we already know it's a minimization problem because it says minimize its cost. Okay? Now, we must figure out the unknowns. 4 unknowns off the bat, we already know that we don't know how many they're making in-house of item A. We don't know how much they're buying. We don't know how many they're making in-house of item B, how much they're buying, and how many they're making in-house of item C and how much they're buying. So sorry, that's 6. Apologies. So that's 6 unknowns. Right? And we can label them such where we can say let X, I'll call it AM, right? Because unit A made equal the number of units of item A made. You could say manufactured, you could say whatever. And XAP equal, I'll put quotations, we'd have to repeat, purchased. So this is the number of units of item A purchased. Then XBM is equal to the number of units of item B made and XBP equal to the number of units of item B purchased. Then XCM equal to the number of units of item C made, and XCP equal to the number of units of item C purchased. Okay? So these are our 6 unknowns, right? If you wanted to, you can make unknowns for the number of Q units used and the number of hours used, but that can just be done within your equations as well, or inequalities, sorry. So I'm just going to do it that way instead. So we're going to be minimizing Z, and remember we want to minimize the cost. So first let's deal with the hours. We know for each hour we're paying $20 per hour. So we're going to put 20. And within here, obviously, if you were to do an unknown for hours, it would just be like 20H, right? That would deal with hours. Okay. But we're going to do it ourselves just to better understand it. So for item A, it requires 2 hours of labor if it's made. So that's going to be 2XAM. And now for item B, if it's made, requires 6 hours. So 6XBM. And then for item C that's made, it requires 3 hours. Okay. And that takes care of our hours, right? Because purchasing it doesn't use any hours, right? Because we don't know if like we're going to pick it up or we're like shipping it. Most likely we're shipping it, so it's not using any hours, okay? And so now we have to do the units of Q. Each use $5 per unit. So that's going to be plus 5. And we need to say, okay, how many units does it take to make a unit of item A? Well, it takes 20. So that's 20 XAM. Okay. Item B requires 15 Q units. So 15 XBM. And how much does item C require? Well, item C requires 22. So 22. Ooh. Sorry. 22XCM. Okay. So this is our Q units, right? And to the left of it is our hours. Right? And you might think, okay, well, looks like we're done here. Let's move on to our inequalities. You would be incorrect, right? Because we also need to take into account the cost incurred when we purchase from our wholesaler item A, item B, and item C. Well, for each purchase of item A, it's $200. So we're going to say plus 200 XAP, right? That's the number of units of item A purchased. Then for B, unit of item B, it's 265. So we're going to do plus 265 XBP. And then finally for C, it's 235. So we go here plus 235 XCP. Okay. And this should work for our objective function. Okay. Give me 1 second. Okay. Sorry about that. So now we can get to the such that's, or subject to's. So subject to, well, we need to take into account our limitations. We know that we only have 4,000 hours of labor available. And for each unit of item A, B, and C we create, we incur some number of hours. Okay, where for item A, we incur 2 hours of labor. So we could say 2xam plus, for item B, we incur 6 hours of labor. Actually, wait, we wrote it up here. What am I doing? 6 bm. And for item C, we incurred 3 hours of labor. Right, so plus 3xcm. Right? But remember, we're not using exactly all 4,000 hours that we have. Or, yeah, 4,000. We're not using exactly all 4,000 hours that we have. It doesn't say that we're using exactly 4,000. So it's going to be less than 4,000 hours. Okay. Now, ensure, let's say that instead it says company X has available 4,000 minutes. You need to make sure that when you're making your inequality, you must convert it to hours. Right? Minutes to hours, that's just the number of minutes divided by 60. That'll get you your hours. So make sure that they're in the same type. Okay? So this should be for the hours. Now, for the units, we have 5,000. Right? So to make a unit of item A, it's 20 Q units. So 20 XAM. For item B, it's 15. So 15 XBM. And then for C, it's 22. So 22 XCM. And remember, we said that we have 5,000. So here, we're going to put 5,000. Okay. And at this point, you might think, oh, okay, we're done. We're not done. Because we have one more limitation. Company Y wants 300 units. And then they want 450 units of item B and 380 units of item C. Right? So 300A, 450B, 380C. Right? So the combination of how much we make plus how much we buy must be equal to their demand. Right? So for item A, they want 300. So XAM plus XAP must be equal to 300. XBM plus XBP. Well, what does that have to be equal to? I think we said 350 or 450. And then XCM plus XCP, that must be equal to 380, I believe it was. Let me just double check. Yep, 300 units. Okay, and again, all that's doing is it's combining, again, the number that they made plus the number that they bought wholesale, right? Because you could think of them like as some wholesale distributor. or not a wholesale distributor, they're just a store, right? And the company's trying to buy from the store. The store is able to buy items wholesale, right? So they're just adding up the number that they've bought plus the number that they've made, and they're setting them equal to the amount that that the company wants. Okay? All right? And then again, at that point, you might think, okay, well, now I'm done. No, you're not. You're not done because you must ensure that each variable that you use is greater than or equal to 0. So you could say x am x. Actually, I'll do it this way just because it's easier. I'll do x I j is greater than or equal to 0, where I is equal to a b c and j is equal to m and p. Okay. And from here, now you're done. Right? Where you ensured that each number, anytime you see a number in one of these questions, you must ensure that it shows up in here somewhere. So 4,000 is here. 5,000 is here. 20 is here. 5 is here. 235 here. 265 here. 200 here. 22 here. 15 here. Yeah, so like you just have to ensure that each number you're using shows up here, right? Now let's say you wanted to use the unknowns instead of calculating this math. Then you could have said like H is equal to the number of hours used and Q is equal to the number of Q units used, right? In that case, it would have been 20H plus 5Q plus 200 XAP plus 265 XBP plus 235 XCP, right? Then from here you would have said H is less than 4,000, Q is less than or equal, H is less than 4,000, it's less than or equal to 4,000, Q is less than or equal to 5,000, but then you would have also had to say 2XAM plus 6BM plus 3XCM is equal to H, and H is equal to 2XAM plus 6XBM plus 3XCM, right? And Q is equal to 20XAM plus 15XBM plus 22XCM, right? So either way, you still need to do that math. If you do it this way, it's 4 less lines you have to write, but less math. This is 4 less lines you have to write, but it's more math. But that math that you're doing is just a copy, so like it's not exactly more math. It's just like instead of writing one letter, you write letters and numbers. That's pretty much it. If you do it with the 2 unknowns, that's 4 extra lines because you need to write the 2 unknowns, and you also need to write over here like H is equal to 2XAM plus 6BM, 3XAM, and Q is equal to 20XAM plus 15XBM plus 22XCM. Right? That's something that you need to do. Right? And then over here you would also have to do H is greater than or equal to 0 and Q is greater than or equal to 0. So it's completely up to you what you want to do. You just have to make sure you're doing it right. So I'll leave that to your judgment. Whatever makes the most sense to you. This personally, I like the most. So yeah.
Wait, that's it for the question 3?
Yeah, this is all you need to do.
Not gonna lie, the last 2 questions are 3 points.
You said what?
I was saying the last 2 questions are 3 points.
I wouldn't say the last 2. I would say first and third are 3 points. The second one is you can get anything. The second one you can get something that you just like, you don't even know, and like you just like can't even answer it. First one is pretty easy to answer. and it's 60 points. So I would say first and third are free, and second is like kind of RNG, unless you absolutely know your stuff. But I doubt all of us do. So
Yeah.
I would focus number two, me personally. And then with number three, I would focus the different situations that you can get. So, like, let's say you get the distribution situation where you need to make like a box with like you have like supply and demand
Oh, I know
and
what
some
you mean.
numbers here, right? So that's one of the situations. You should know how to do that. All the different situations that might show up, the three different situations plus this, you now have knowledge of. Where this is one situation where you have the choice of the hours and the Q units, right? You have the choice of either using an unknown or not. That's one option. And then the other situations, those are given on the practice exam that she gave, right? So you can practice those there by just taking a screenshot of the questions she gave, put them into GPT, and just say, give me more examples or give me more questions similar to this. So, like, if I go to GPT, I believe I already did it. Um, let's see. Yeah, like for example, over here, I put the ones that she gave, 1, 2, and 3, right? And I said, give me more questions similar to these. First one was pretty much the same situation as the first one. This was the distribution or transportation problem, right? Where you need to make the diagram, right? Where all the companies are all the warehouses are on the left side of the diagram, all the stores on the top. So pretty much similar to this. Then you would write supply over here, and then demand over here, and then just put that. And then you would have like XA1, XA2, XA3, XA4, XP1, XP2, and so on, right? That's something else you have to do. Um, Packing for a trip, this is another one. So, you know, these are just the different situations. If you just take these questions, first of all, do these questions, right? Once you do these and you're comfortable with these and you get them right, go to GPT and say, give me more. Once you get more and you're able to do these without referencing back to these to see like, okay, how did I do it this way? Or how did I do it in this question? Once you do that, you'll be set for number three, right?
Yeah.
For number one, you can do the same thing. I'm pretty sure I did the same thing. Um, yeah, so with number one here as well, I said, make me a practice similar to this one. Ensure that when solving LP problem in number one by the simplex method, the problem is already in basic feasible canonical form. Because remember, she said you're going to have the question you're going to be given will be in that form. So I said, okay, give me a question that's similar to that. I did this, and now I'm perfectly fine with number one, right? So if you do that for number one and number three, you'll be fine. Number
Okay.
two, it's a bit different because it likes to just give like the same question from before, but like different letters sometimes, or like a different. I don't really like what it does here. Like here it said something else. Here I was like, make a new one. It gave me this. We've never worked with like squares in it, so like I just didn't even do this one. I did this one but without the squares. Um, and this was pretty easy too. But for number one and number three, you can study using GPT. Number two, you just gotta have to know your stuff. That's all I can
Yeah.
really do. Yeah.
Okay.
All right.
Right.
But yeah, that's pretty much everything I had to go over. I saw someone just joined. Rojas. Yeah, we just finished up. But I did record it, so you're good. Um, it's still recording, right? Yeah, okay. It's about to hit 2 hours. But yeah, this is pretty much it. I will send this exam here. I'll do that right now, actually. Holy fuck, I have to clean up my folders. Okay. Okay. Here is the exam. And here are the solutions. Obviously, use these, but I would suggest not making her aware that we have these. She's fine with us having them, but if she knows that we have them, then she's not going to potentially reuse those questions, and we might get something even crazier for number 2. So don't go up to her and say, hey, can you, explain this question when that was something that was on the exam, and she's going to know that you guys have it. That is something that people have done for other classes like Obrenic, and people got fucked over because of it. So don't do that. I'm trusting you guys since I gave it to you. Don't do that. And yeah, that's pretty much it. Feel free to reference my answers when looking at the solutions too. I will send this as well. Can I not just download it? Export. PDF. Save. Okay, give me a second. Upload a file. Okay, for the people watching, it's in the resources chat, the Math 247 Discord. I'm going to send my solutions there as well, so you can feel free to reference it. But if you're going to use it, I would recommend opening it in Whiteboard so you can zoom into it and stuff, because it's pretty small. But yeah, that's pretty much it. Any questions from either of you two, or are we all set?
No. Thanks so much.
Yeah. All right, so I'm going to end the recording, and if any of you guys have questions that are watching it, feel free to message me on Discord. And yeah, so let me end this.